Okay, so now let's talk about the Zeroth Law of Thermodynamics and define what that is. So in a situation where you have a hot substance at some temperature, some initial hot temperature Ti, and you have another substance at some initial cold temperature, blue Ti, the idea is that when these two objects at different temperatures come in contact with each other, what happens is that the Zeroth law of thermodynamics tells us that the flow of heat will happen from the hot substance onto the cold substance. And since the hot substance will be losing heat, its temperature will go down, whereas the cold substance that will be accepting heat will have its temperature go up. And this procedure will happen until the final temperatures of both objects end up being the same value. All right. So this state in which the final temperature is the same for both is known as thermal equilibrium. And simply put, the hot substance lost heat, and that means that its initial temperature is going to be larger than the final temperature at which it will be held at thermal equilibrium. And on the other hand, for the substance that gained heat, the cold substance, the initial temperature is going to be lower than the final temperature. And so this final temperature is actually going to lie somewhere in between the initial temperatures of the cold and the hot substance. But the heat flow will take place from the hot substance onto the cold one. All right, so this is the Zeroth law of thermodynamics. Sometimes that gets omitted in textbooks, but it's kind of understood and to happen that way because of all the other aspects of thermodynamics that we'll be discussing to some extent in this class. So let's do some examples and see how we apply the Zeroth law of thermodynamics. Now, in regards to this law, unlike the calculations we did before with water, where we simply raise the temperature of the water or we decrease the temperature of the water and we simply calculated the heat associated with water, here we're going to do something different. We're going to have a hot substance being mixed with a cold one. And the way you tell which one is the hot substance and which one is the cold substance is by looking at the temperatures. The hot substance will have the higher temperature. The cold substance will have the lower temperature. So in this case, the aluminum bar, 10 grams aluminum bar, is the hot substance at 75 degrees Celsius, and the 100 ml of water being held at 25 degrees Celsius is your cold substance. Now we want to find out the final temperature of this mixture once thermal equilibrium is reached. And in order to do this, we have to be given the heat capacities, the specific heat capacities of water, 4.184, and of aluminum, 0.900 joules gram degrees Celsius. All right, so this is the way the problem differs a little bit from your typical Q equals MCAT problem. You have two types of heat involved in this process, and the Zeroth law of thermodynamics tells us that the hot substance will give heat away to the cold substance, and the overall exchange of heat is going to be the same magnitude for both the hot and the cold substance. But whereas the hot substance is losing the heat, the cold substance will gain it. So notice that we have this negative sign in front of the cold substance to symbolize that heat lost by the hot substance is gained by the cold substance. And this entire premise, which is technically speaking the Zeroth law of thermodynamics in equation format, is what we'll use to solve the problem. Alright, so what we need to do now is rewrite Q hot and Q cold in terms of MCAT. Specifically, we'll have the mass of aluminum, the hot object, multiplied by its specific heat capacity, multiplied by its final temperature minus the initial temperature. And the same thing is true for the cold substance. We'll multiply the mass of the cold substance by its specific heat and its change in temperature, T final minus T initial. But make sure that you input this negative in front of Q cold. If you forget to introduce this negative, you will mess up the problem and you might end up with some answers that are completely nonsensical, like ending up with temperatures that are higher than what you started with. Like, that's not going to happen. So be careful not to forget, be careful to forget that negative. If you do that, you're kind of done for. All right, but now what we're going to do is we're going to input the values. So we have the mass of aluminum, the hot substance, 10 grams. The specific heat capacity of aluminum is 0.900 joules gram degrees Celsius. The final temperature is what we're looking for, so we don't know. We just keep it as T final. And the initial temperature is 75 for aluminum, so we use 75. Notice that I'm not using 25 because that belongs to water. So now for water, we have 100 mLs, which in the absence of density data, we assume to be equal to 100 grams of water. So we have 100 grams of water multiplied by the specific heat capacity of water, 4.184 joules gram degrees Celsius, and we multiply by the final temperature, which we don't know, minus the initial temperature of water, which was 25.0 degrees Celsius. All right, perfect. We have the setup. Now, what I would recommend doing, because the units can get a little nasty trying to solve for T final here, what I recommend saying or doing is simply taking hold of the fact that you have an equation on the left where you're multiplying by grams, equation on the right where you're multiplying by grams, equation on the left multiplying by joules grams degrees Celsius, equation on the right multiplied by joules grams degrees Celsius. So simply stated, cancel all those units out, get rid of them. Don't even worry about it. In fact, what this will tell you right away is that the final temperature is going to be in degrees Celsius. So it's actually simplifying the process very nicely for you. Okay, now what I'm going to do is I'm going to multiply 10 by 0.9 to get a value. And I'm going to multiply 100 by 4.184 to get another value. Okay. All right, so we're going to have 9 times TF minus 75. So if you distribute the 9 by TF, you get 9 TF. And if you distribute the 9 to the negative 75, you'll get negative 675. Same idea here. 100 times 4.184 is the same thing as 418.4. Multiply that by TF and multiply that by negative 25. We're going to get negative 418.4 TF and positive 10,460. Now, notice that I'm not only distributing 418.4, but also the negative along for the right. Okay. Okay, now what happens is that we move all the terms with TF to the same side. We move all the terms without TF to the opposite side. So that means that we add 675 to both sides, and we add 418.4 TF to both sides. And that means that 418.4 plus 9 is 427.4, and 10,460 plus 675 yields 11,135. So at this point, all you need to do is divide both sides by 427.4 to find out the final temperature, which in this case is 26.5 degrees Celsius. And the big point that I need to restate and make is that the final temperature lies in between both of the initial temperatures. So 75 and 25 are definitely the endpoints compared to the final temperature. The final temperature is in between those two initial temperatures. That's what you want to see. If you end up with a T final that is greater than either of these temperatures, you made a mistake. If you end up with a T final that is lower than either of these two temperatures, you also made a mistake. This temperature has to be in the middle. All right, let's do another example of the same kind. All right, here we have 50 grams of gold, a gold ring, that have been heated to 160 degrees Celsius. We're dropping them on 250.0 mLs of water, which have been held at 70 degrees Celsius initially. The final temperature of the mixture is 17.88. So here we're being told the final temperature. What we're going to find out in this problem is the specific heat capacity of gold. And in order to do that, we need to know the specific heat capacity of water, 4.184 joules gram degrees Celsius. All right, so needless to say, we have a substance at a higher temperature than a second substance, so we have Q hat equals negative Q cold. If we rewrite the Q's into MCATs, we get the two following equations here. And now we input the values. So we have 50 grams for gold times the heat capacity, which we don't know. We're going to find that out in a second. The final temperature we do know is 17.88, so we input that in here, minus the initial, which is 160 degrees Celsius. All right, now we're going to equal that to negative mass of the cold substance, which is the water, so 250 mLs, which is going to equate to 250 grams. The specific heat capacity, which is 4.184 joules gram degrees Celsius for water. Final temperature is still 17.88, but the initial for water is not 160, but rather 17 degrees Celsius. So make sure not to make that mistake. Alright, so as I said before, the grams will cancel out on both sides, and your degrees Celsius will cancel out. So all you'll end up with is joules, grams, degrees Celsius, which is the units for heat capacity. Alright, so what I'm going to do now is carry on the subtractions, and I'm going to multiply the change in temperature by the mass, at least on the left side of the equation. So the change in temperature for the left side is negative 142.1. The change in temperature for the right side of the equation is 0.88. Multiplying negative 142.1 by 50 yields negative 7106, and multiplying 0.88 by negative 250 and 4.184 yields negative 920.48 joules grams degrees Celsius. So at this point, you just need to divide both sides by negative 7106, and you'll find out that the heat capacity is 0.1295 joules gram degrees Celsius. Alright, and I have one more example to show, but this one's a little bit more convoluted, so I'm going to save it for the next video. So let's stop at this point.